Hello! Today, as a continuation of the topic chemical equations and reactions, we're going to be working on this type of assignment. This is a translation of a verbal equation, which you can observe in this graph, into a chemical equation, which is represented by symbols of chemical elements, and as a result, we will be creating formulas, and it is imperative that the equation is balanced in this particular context. Alright, the first example involves the interaction of sodium carbonate with hydrochloric acid. The reaction leads to the formation of sodium chloride, water, and carbon dioxide as the end products. Alright, let's translate into the language of chemical formulas. Sodium carbonate is a salt, which consists of sodium and the acidic residue CO3. But we gotta check the formula, you know. So we will establish the charges. Sodium plus CO3 2 minus. Consequently, the formula for sodium carbonate is sodium 2, CO3. Hydrochloric acid is the abbreviation for HCl acid. This is a chemical reaction known as a double replacement or exchange reaction, and as a result of the reaction, sodium chloride is formed. Well, I guess you already know the formula for sodium chloride. It's a commonly encountered substance, but you can also check it through charges. So, moving on to the second item, we were informed that it would be water, and the third item in the reaction is expected to be carbon dioxide. So next we unquestionably have to equate this interaction because we are unable to leave the equation unbalanced and without resolution. Alright, let's start with sodium. On the left side there are 2 sodium atoms, on the right side there is 1. Prior to the NaCl formula we placed the coefficient 2. Currently we have 1 chlorine on the left side and 2 on the right side. So, past the chlorine, we'll set the coefficient to 2. Next, let's switch to hydrogen. There are 2 hydrogens on the left side and also 2 hydrogens on the right side. Just gotta check the oxygen now. On the left side, there are 3 oxygens. On the right side, there are 1 and 2, also 3. The equation turned out like this. Let's read it. Na2CO3 plus 2HCl equals sign 2HCl plus H2O plus CO2. In the next example, sodium reacts with water to form sodium hydroxide while releasing hydrogen gas as a byproduct of the reaction. Okay, sodium is a basic substance, a metal, and in this particular situation it reacts with water. This is a straightforward substitution reaction, and sodium displaces hydrogen. In this particular instance, we obtain sodium hydroxide, sodium, wow. We can verify this formula by examining the charges. If it appears incorrect to you, you can certainly investigate it. The second one will be highlighted as hydrogen gas. Now we need to check. We start with whoever has a higher index value in the list. Since sodium is on the left, if you look on the right side, it is the same. Let us start with hydrogen. But be aware, there are 2 hydrogens on the left and 3 on the right. Then we will apply the principle that we have already mentioned to you. On the left side is an even number of hydrogen, on the right is an odd one. Then we'll put a coefficient of 2 in front of the sodium H formula, so that the number of hydrogen in this formula becomes even. So in total there are a total of 4 hydrogens, and on the right side there are a total of 2 hydrogens. So prior to the water formula we will place a coefficient of 2. Incidentally, we can also verify the oxygen. Here is his oxygen on the left side too. If we emphasize its order, here it is the second in line. He has 2 on the left and 2 on the right. Sodium remains. Okay, since this equation is more complex, let's emphasize the alignment sequence. On the left side there's sodium 1, and on the right side there's 2 of it. So we'll have to put a coefficient of 2 in front of the sodium formula. Our equation is equated. 2 times 3 plus 2H2O equals 2 times 3 OH plus H2. Moving on to the third example. Here, iron oxide with a valence of 3 reacts with nitric acid, leading to the production of a chemical compound. As a result of the reaction, iron nitrate 3 is formed, and once again, the product of the reaction will be water, just like in the first case when there was also an exchange reaction. That is the exchange reaction, so the substance that was claimed to be the original substance is actually iron oxide. But be aware, for this metal, they informed us that the valence is 3. So if we go by the valence factor, that indicates that iron possesses a valence of 3 and Kestorod possesses a valence of 2. And by using the rule of the cross, we are able to determine the indices of ferrum 203. Next up is nitric acid. The formula for nitric acid you definitely got to know, just like hydrochloric acid too. As a result of the reaction, an exchange reaction occurs. So like if it works for you, and in this context, by the way, it would be really uncool to put such a restriction. It's totally possible even in this situation. So we can also put it here. And mind you, what's left outside the frame, connected and intertwined here, while inside the frame right here. However, it is true that carbonic acid is decomposing. So what is the deal here? Thus, we are informed that it turns out to be iron 3 nitrate. Therefore, the valence of iron is 3, and due to the fact that hydrogen in this particular situation is 1, the valence of the nitrate residue No3 is 1. Then, as per the rule of the cross, ferrum No3 3 times, and obviously water. Reminder, for exchange reactions we follow a scheme. Let's start by ironing out the first thing. The iron is on the left side 2, on the right it's 1. Before the ferrum formula, we'll multiply by 2 3 times. Now let's calculate No3. No3 here is 1, and on the right of it, let's see, it's 2 multiplied by 3, which results in 6. And on the left, T is number 1, so we set the coefficient to 6 before nitric acid. Now let's discuss hydrogen. There are 6 hydrogens on the left and 2 on the right. Therefore, prior to the water formula, we place a 3. Check O22, 3 O atoms in oxide, also 6 and 3. We have 18, 18 plus 3, 21 O on left side, 18, 3, 21 O2 left. On the right side here, there are 9 of them, 2, 18, and another 3, also 21. And I will remind you once more that in this regard, if you are truly uncertain whether you have balanced it correctly or not, you can write yourself a hint for each element on the left side of the reaction equation, as well as on the right side. For example, how much iron on the left? Hardware on the left is 2. How much iron on the right side? Located on the right is iron 2. Please proceed. As an example, consider nitrogen, for instance. On the left side, we have 6 nitrogen when we balanced it. And on the right side, there's also 6 nitrogen. Now, onto the next hydrogen. There are 6 hydrogens on the left side, and there's also 6 hydrogen on the right side. Now all that's left is oxygen. We have computed the amount of oxygen collectively, and it is 21 on the left and 21 on the right side of the oxygen element. In my opinion, you can perform an oral check, but if you're uncertain, I believe having a signature wouldn't cause any harm. Then you can certainly ensure, double check, calculate these indices, count the total number of atoms. And let me tell you, yes, the equation is absolutely correctly written, and most importantly, this equation is correctly equated. Read equation as needed. F2O3 plus 6H3 equals sign 2F3H3 plus 3H2O. Reaction known as exchange or replacement. 3 times plus 3H2O. This reaction is also known as exchange or double replacement. I hope, as we went through these examples, it's clear. And at the next class, we'll continue and go over similar examples again so that they don't confuse you and you can do such tasks on your own and most importantly, correctly. Goodbye.